Um, so welcome back, everyone. We are going to get started with our fourth session, which will be post-CMOS hardware and device materials. So the chair will be Peter Burrell. Peter is a professor in the ECE department of USC. Peter, please.
Yeah, welcome everyone. I hope you can all hear me. This is going to be a great session. Our first speaker is Jayakanth Ravichandran. He's an associate professor of chemical engineering material science, as well as a professor in the electrical and computer engineering department. And he's going to be more on the material side of things, and look forward to his talk. So I'll give it to Jay.
Thanks, Peter, for the nice introduction, and thanks a lot for this opportunity. I'm going to get started and try to give a very big picture view of why we need to think about novel materials for AI-related applications. So I'm showing three different graphs. I'm going to go from the left to one by one to emphasize this idea. On the left, we see the total electricity consumption in the world. This is in terawatt hour on the x-axis, on the y-axis, and you can see that we are somewhere in the 20 to 25,000 terawatt hour consumption. And on the bottom, I'm showing a plot of what is the electricity footprint for the communication technology. If we keep going as the way we are going, we should hit somewhere close to 8,000 in 2030, and this is going to be roughly about 20% of the total electricity demand that is projected in 2030, which is shown on the rightmost graph. What this tells us is that increasingly the amount of electricity that's being consumed in computing and communications is growing. And worst case, it could even dwarf everything else that we currently use electricity for. I mean, you can see the worst case scenario, it's not 8,000, it's 30,000 in the middle section of the graph. So this tells us that we need to really think about high efficiency, energy efficiency in computing and communication technologies. Next slide. So the most important technology that people have been trying to think about is neuromorphic computing. I mean, as you have heard, various versions of it, all the way from software to hardware implementations. The one plot that really captures how digital technology completely differs from brain is shown on the left, where we compare the power density versus the clock frequency. The brain works at very low power density and also very low clock frequency compared to even the most primitive computing technologies that we have had, like 4004, for example. The biggest advantage for brain is in the connectivity and the parallelization that it achieves. It has 86 billion neurons, 10,000 neurons connected to each synaptic weight that is present in your system. So you need to tackle three main challenges to even try to mimic brain. One is the parallelization, connectivity, and energy consumption. Next slide, please. So how do we go about doing this? I mean, we are fairly limited in how well we can do what brain does, because it's had years to evolve. But the simplest thing that we could try and work with is try to take a phase change material. So if you look at the potential energy landscape for a phase change system, you're going to have two double wells in some order parameter that you can think of, and you want to go between one well to another to get two states in your system. And this well should have sufficient barrier against the thermal energy that is present in your system, but also should have some very low energy impulse that will make sure that going back and forth between the two states is fairly easy. And some of the examples for this would include like metal insulator transition materials, the one that I show in the middle, which is vanadium oxide, which undergoes 4 to 5 orders of magnitude change in resistance over a very narrow temperature range. You can also have something like a ferroelectric material where you can change the polarization state by applying electric field, which is also a very low power consuming mechanism. Now, we came up with a couple of different types of solutions here. I'm just going to highlight two examples. The first example is all about, can you think of a slightly different device design where we took a vanadium oxide channel and typically people used to apply electric current or voltage to switch this vanadium oxide to create an oscillating device where you can go back and forth between the resistive and conductive state. Now, the challenge here has been the capacitance in the system itself, which slows down significantly. Hence, we thought of an idea of putting a very thin metal layer on top, which will ensure that the switching frequency can be much faster, and also you can reduce the energy consumption. Next slide, please. And we did modeling of trying to understand how this device structure would work. So basically, you have a scenario where you're heating your metal layer on the right side, if you pay attention to the graph. And then once you have heated it, you are going to create a phase change on your VO2 layer itself. And that at that point, the resistance of the VO2 layer is even higher than the metal. And hence, the current starts going through the VO2 layer. And then the metal stops heating, and hence the whole system cools down. And then you go back and forth, and you try to switch back and forth between the two states. So based on our modeling, what we found, this was back in 2019, 4 years, it's fairly dated. We saw that we could achieve much lower power and energy consumption, and also very low footprint. The main reason why our footprint is smaller is primarily because we'll work with a 2-terminal device rather than a 3-terminal device like in CMOS or so. So in principle, if you do things right, your scalability could be much better than a typical CMOS system. But we are getting to 3 nanometer nodes, and things are moving really fast in the CMOS side compared to even those when we were trying to think about this model. Now, let me switch gears and talk about slightly. Okay, so this is our very crude effort to try and make an oscillator with this bilayer device structure. In the in-plane geometry, we have achieved one of the highest frequencies that has been reported in the literature. We are still trying to scale down. We are fairly at the large length scale limit. And if we do scale down to tens of hundreds of nanometer range, we can significantly reduce power and oscillation frequency and so on and so forth. But even at this scale limit, we can already see, compared to our simulation, our experiment is underperforming quite a bit, largely due to contact resistances and how we can optimize the device geometry. So this highlights, if we need to keep going down, there's a lot of work to be done in terms of device optimization and so on and so forth. So just to say that, like, even if you think about a novel idea in the material side, takes quite a bit of device engineering, which is very obvious to the crowd. Now, I'm going to talk about slightly different thing. We discovered a new phase change material. This is BATIS3. There are a lot of interesting things about the system, but I want to talk about one very specific thing where you can create both volatile and non-volatile functionalities depending on the state of the system. And that allows you to do a completely different type of computation, which is required in a neuromorphic circuit where you do memory and computing at the same time. So this material has 2 specific phase transitions, transition 1 and transition 2. And in principle, if you stay between those transitions, whether we are in the heating cycle or cooling cycle, we can access 2 completely different behavior, which is what I'm going to capture in the next 2 slides really quickly and try to stay on time. Yeah, so this is the first set. So let's say if you cool down this material, you're coming up in the warming cycle. And when you stay inside the warming cycle anywhere, and if you try to apply a voltage pulse in the system, the material starts becoming more and more resistive, and you can keep increasing the resistance state. And the resistance state can be selected, and it's very, very stable over a very, very long period of time. And we've tried to do this over a few hours or so, and it's fairly stable, and as shown in the bottom leftmost graph here. And this gives us a pathway to create something like a multi-level memory in the system, and we are currently really figuring out how we can go back to this low resistance state, but we can always go from the low resistance to high resistance in a very, very controlled manner. So the other part is what we're thinking. We have some field effect geometry idea to try and solve that issue. The next part is going to be the oscillator, which is the volatile aspect, where if you stay at even 130 Kelvin on the cooling cycle, you can apply a bias and leverage this NDR type switching behavior that we see in transition 2 to create oscillator in the system. So by carefully figuring out what side of state you can set your material in, you can achieve both the memory effect and also the volatile oscillatory behavior. So that gives us, in some sense, synaptic behavior and neuron behavior in the same material at the same temperature. Unfortunately, these things happen in cryogenic temperatures, but increasingly there is a lot of interest in even cryogenic computing. So, so mimicking this in a material that works at room temperature is another challenge. So just to give a conclusion and outlook, mimicking a brain and hardware is a challenge, multi-scale challenge. Power, energy, parallelization, connectivity, these are all three big bottlenecks. We are primarily addressing the power, energy, maybe a little bit of functionality issue, but the parallelization connectivity can only be done if we try to work with the simplest possible, like two-terminal type geometries. And this also needs a lot of co-design approaches. So like interaction from all the way from materials to circuits and systems is needed for us to do this. And most of the work that I showed today were funded by Army Muri program. So I would stop here. Thank you.
Let's move on to our next speaker. We'll take questions at the end, though if you do have questions, please put it in the Q&A and queue it up, so I'll be ready to ask them to the speakers. Our next speaker is Professor Rehan Kapadia. He's a professor in our electrical and computer engineering department, and he's going to continue the discussion on oscillation-based computing.
Yeah, thank you, Peter. And I hope you can hear me. Just
yeah, we can.
All right, fantastic. So, Jayakanth gave a great talk about why power consumption is a major issue, and one approach to potentially reducing that is using brain-like computing. I'll maybe give another flavor of this, and I'll introduce it a little bit differently. If you look at this slide, this is the number of floating point operations it takes to train notable AI systems. So I really only want you to have one takeaway from this, and that's for today's modern AI systems to just go through and train the system once. It takes on the order of about 10 to the 24 floating point operations. That's such a large number that, to put it, I mean, for example, there's 10 to the 25 molecules in the body, but that's not a good comparison. So if you go to the next slide, I thought a good way to kind of put this into context is that, say we take the world's largest supercomputer. This is from last June. This has actually been updated, but we're using the numbers from last June. Say you take the world's largest supercomputer and you want to train one of these large systems, it would only take about 250 hours of training, which, about a week. That's not bad at all. But if you look at how much power it would consume, it's about 6 million kilowatt hours, which is about the same. The energy it would consume is about 6 million kilowatt hours, which is about the same amount of energy as about 500 houses over a year. So this is a serious challenge, and it's not just a theoretical serious challenge as to what might happen in 10 years. It's right now. I mean, this is a huge amount of power that people are using. So one of the main things that we want to do, for example, at the edge, is apply algorithms such as convolutions for machine vision. So a convolution algorithm is a very powerful convolutional neural network is a very powerful algorithm that allows really, really accurate machine vision. And so if you look at the way that these systems work, is you have an image that comes in. So this is kind of represented by the input data, and then you run a bunch of different filters over that image to create a set of feature maps. And so you have a large number of feature maps, and then you continue to do that until you put it into a classifier, and you get the various information that you want out of that image. So this is extremely powerful, but it's very computationally expensive. So if you go to the next slide, an example, if you had a 1024 by 1024 image, and you wanted to just create the first set of feature maps, and you had, say, 96 feature maps that came out of it, and they were maybe large feature maps, 11 by 11 pixels, you would use about 30 billion operations to do that. And that's a lot. However, if you go to the next slide, that's fine, because we have GPUs like this NVIDIA A100, which, it absolutely can handle it. However, we're talking about AI on the edge, and so we can only deploy so many $80,000 GPUs at the edge. That's basically where it is. So what people are trying to do use different types of hardware-based approaches to accelerate this. One approach for that is in-sensor processing, where what people will do, and this is from the literature, this is from a Nature paper in 2020, what people will do is essentially they will integrate the multiplies and accumulates directly into the hardware. And so one example of how you might do that, as shown in this paper, is where you modulate the responsivity of a photodetector itself. So you can create a camera where when you take the picture, you don't just get the information, you get the information multiplied by a number. And then you can actually take the currents that are coming out of each pixel, you can add them together and you can get the results that you want. So if you go to the next slide. And that's essentially what it allows you to do is it allows you to take your image and it allows you to create one processed image from that. If you want to create more processed images, you need to expand the hardware. So what we're trying to look at is we're trying to say, hey, can we use oscillations so that we can take an input image in and then simultaneously get all of the processed images out that we would like. And that's kind of what we're showing on the bottom. So we have a device that we're using to do that, to do this. It's not unique in the sense that this is not the only way you can do it. You just need oscillations, but we're creating oscillations using this device. And essentially the way that we do this is to take a semiconductor substrate such as silicon, put a metal mesh on there, put graphene on top of it, and it gives you this negative differential resistance when you shine light on it, and it doesn't give you a negative differential resistance in the dark. So when you add an inductor to that, you get spiking behavior. So you shine light on it and your device starts to oscillate, and you don't shine light on it, you don't get any oscillations. If you go to the next slide. And so this is just kind of showing that as you change the intensity of the light, the spectrum of the oscillations or the frequency of the oscillations change. And now that's important because what you can do, if you go to the next slide, is you can then take that device and you can connect it to, say, a bandpass filter. You can connect to some kind of frequency-based filtering. And what that allows you to do now is it allows you to extract information out of these oscillations from different parts of the spectrum. And so essentially what we can do is we can say, hey, all right, now that we have some amount of power falling on our device, if we put, for example, a bandpass filter with some center frequency F0 and some bandwidth delta F, what we will end up with is we'll end up with a power filter, meaning we will get information about the power that was coming into the device. Now, of course, you get that with even, any kind of photodetector. So a single device is not interesting. If you go to the next slide, what you can do is you can kind of see what kind of different powers you get out of there based on frequency and based on bandwidth. But if you go to the next slide, now what you can do is you can couple two of them together. And when you couple two of them together, what ends up happening is that you actually start to define functions on the inputs. So this is an example of just two oscillators coupled together where you have power 1 falling on oscillator 1, power 2 falling on oscillator 2. And then as a function of the frequency and the bandwidth of filtering, as well as the coupling impedances, you actually define different functions on the inputs. Now, the key thing about this is, especially on the right graph, is that what we can do is we can couple oscillators together. And by looking at different parts of the frequency spectrum for the output of those oscillators, we get different computations carried out on the input. And that happens simultaneously. So go to the next slide. This is a simulation example where you take a 2x1 oscillator and you kind of slide it over the image to create different types of feature maps. And essentially what we're showing is that by taking the output of these devices and filtering it at with different frequencies and bandwidths, you actually get different feature maps out. Now, this is feature maps that come out of the same oscillation, it's the same output oscillation curve. So if you go to the next slide, the way that this works is essentially it's a overlap between the function that you defined on the oscillator with your coupling of the oscillator and the actual the values of the pixels in the image. And so essentially, the reason you get three different outputs is here because you define three different functions, and those three different functions highlight different types of images. So now if you go to the next slide. Now that was simulation. We've actually done this in hardware. We've built a 3x3 array of these oscillators. This is just this showing the kind of how we couple them together. It's not critical. I mean, it is critical, but it's not critical for the overall story here. And essentially, what we do is then we can project images onto this 3x3 array. We can slide it over. We can get the IT curves out, and we can filter them. If you go to the next slide. And now what you can do is we can take that same image, and by using this 3x3 array, we can simultaneously do something like edge detection, intensity filtering, image sharpening, or object segmentation, essentially all done in with the same output stream, just depending on how you filter it out. And so this is another example of a hardware demonstration of a image with two dogs and a cat, and we've kind of shown how by looking at different frequencies and different bandwidths, you can basically choose the dogs and the cats, et cetera, et cetera. And that's all we have time for. But essentially, you can also use this as part of a convolutional neural network, and when you do that, you get improved accuracy. All right, so thank you, and I guess we'll have talks after the questions after the talks.
We'll do questions afterwards, so please post your questions on here. Thank you very much, Rehan. So our next speaker is Joshua Yang. He's also a professor in our electrical and computer engineering department, and will talk to us about memristors.
Thank you, Peter. Can you see my slide?
We can. It's perfect.
Great. Okay. So yeah, this time slot was initially scheduled for Han Wang, who unfortunately told us in the last minute he couldn't make it because of travel. So I decided to use the time talk about memristors for edge AI. So for those who do not know memristor, basically you can think it as a resistor, but with memory. You can electrically change the resistance of the device. It's a two-terminal device. As you can see here, at each crossing point, you have one. You can put them into an array like this. It's a memory array. It is also naturally a neural network. So using such neural network, we have been using for edge AI, which can be categorized into three groups. In the first group, we are mainly trying to use it to build machine learning accelerators to accelerate vector matrix multiplication with orders of magnitude higher throughput and energy efficiency over the state-of-the-art CMOS. And in this case, we just use it as a static memory device. But the device is also capable of very interesting nonlinear dynamics, which allow us to use it to build artificial synapse, artificial neurons, artificial dendrites. Then we put them together to build a neural network, which is more biorealistic, with which we can implement neuroscience principles for more advanced learning, such as unsupervised learning with more advanced intelligence. In the third category, we are mainly trying to build a tool set for intelligent systems. For example, essentially, you can use 2 nano devices to build the most compact intelligent sensing system. You have a sensor, you have a memristor as a processor. These two talk to each other in analog domain without ADC, DAC. And if the sensor output is a voltage or current, it can even power the system. It could be a self-powered system, and so on and so forth. I think, in order to implement all this, we needed to build a large crossbar array. About 5 years ago, we built this, the largest array, 128 by 64. The CMOS part was done in a fab, and the memristor part was done in the university lab. So this is the wafer, zoom in over the circuit, zoom in over the cell, and the device. And with this, we can freely program the device for different applications, such as image compression, such as supervised learning for image classification, And we use it as a kernel for convolutional neural network for video processing. And we use it to classify gates as a long short-term memory network and also convolutional LSTM. We use it to accelerate reinforcement learning, so on and so forth, with such an array. And in the latest advance, we actually made the array with almost 10 times larger, 256 by 256, which is close to a real application. Actually, it can be used in real application now because it's not only made in the fab, in a university lab, but also made in the standard fab for both the CMOS part and the memristor part. And so this is experimentally, we programmed the 256 by 256 array using the on-chip driving circuit. And in an analog fashion, as you can see. So this basically shows the device, the wafer we make has a great uniformity across the entire wafer. And it's really ready for large volume commercialization based on this yield and uniformity. So for edge AI application, we are going to distribute those arrays to customers, millions, billions of them. So in this case, it is not really practical to train every one of the array from scratch. So a more practical way is to really train it in the cloud, then download the weights into the crossbar array. So basically you write the weights in the conductance of the device. In order to make the millions, billions of the array similar to each other with identical weights, with uniform performance, one requirement is that the device needed to be really analog with many, many conductance levels, so you can write the weights in them accurately. But previously, the device does not have so many conductance levels. The most is probably 200 conductance levels per device. The reason is that at each resistance level, you have a relatively large fluctuation, noise. And then you cannot put another resistance level next to it closely without overlapping. So we understand what's going on with the noise at the physical mechanism level in our recent study. So that allows us to develop a protocol to easily denoise it. You can see after denoise it, it becomes very stable with a low fluctuation. Then you can put many different resistance levels close to each other and still distinguishable. So this allows us to have a demonstration of more than 2048 resistance levels, equivalent to 11-bit per device. And that make this edge AI application practical. I guess to summarize, I hope I conveyed the message. Memristor can enable low energy and high throughput AI. We have recently demonstrated 256 by 256 arrays fully integrated on CMOS with the driving circuit underneath the memristor array, which on the device, memristor has shown 2048 conductance levels, which is equivalent to 11-bit. That's the highest among any type of memory demonstrated so far. This is we can do that because the fundamental understanding of what's going on with the switching mechanism. I guess I'm going to stop here with 1 minute left for Wei.
Right.
Thank you for your 1 minute.
Yeah, so our last speaker is Wei Wu. And let's see here. Give me 1 second. Yeah, so.
Can you hear me?
Yeah, we can, Wei. So yeah, you're also a professor in the electrical and computer engineering department. And take it away, Wei. We'll learn about memristors and robots.
Hey, thank you, Peter, and good morning. And okay, we have been in today to talk about AI. The hardware of AI is basically an artificial brain. Then since it's artificial brain, so let's look at human brain. Human brain consists of three parts. Cerebellum, which is the small brain, cerebrum, which is the big brain, and also stem. And stem is in charge of the heartbeat and the breath, and who cares about those, right? Then let's look at big brain and small brain. And so far, most AI applications or the hardware of AI are basically focused on making artificial big brain. And we want to look at something from slightly different angle. And of course, big brain is very useful, it's the most powerful thing. And we want to start with something relatively easy. So we look at the small brain. So what does small brain do? Small brain basically keep people in balance. How do you stay in balance in two functionalities? Sensor fusion and basically all the signal sensors of body got synthesized, so you know whether you are leaning to the left, you are leaning to the right. And then there's a control algorithm. If you're leaning to the left, you push to the right. If you're leaning to the right, you push to the left. And this actually turns out, well, first of all, why human brain evolved into this way? Well, because the requirements for the big brain and the small brain are very different. For small brain, actually, turns out small brain can be a perfect, artificial small brain can be a perfect application for analog computing. While people talk about analog computing for many decades, and there's many advantages, fast, low power, etc., etc. But nothing really happened. The reason is analog computing doesn't have enough precision, not like a digital computer. You can have as many digits as you want. But analog computing, the precision is basically limited by your signal to noise ratio. However, for small brain, do you really care about you are leaning to the left by 1 degree or 1.1 degree? You don't. But on the other hand, you really care about the speed, latency, and the power consumption. Therefore, the artificial small brain actually is a perfect application for analog computing. And of course, actually, 40 years ago, people already proposed to use analog computing to implement small brain for robotic system. Again, nothing happened. The reason was we didn't have a device to implement those artificial small brain in a straightforward way. But now, of course, we have the answer. The answer is memristor. And next slide, please. And Professor Yang just gave very nice talk about memristor, so I don't need to go through details. Basically, it's a two-terminal device, and it can be programmed to different conductance value. Next slide, please. And so now we have the nice memristor, so we actually implemented an artificial small brain based on memristor. So we implement the small brain for the simplest possible robot. It's a basic self-standing car. You only have 1 degree of freedom. So in this car, you see there's two on top. There are 2 circuit boards. One of them is for the sensor fusion. The other is for the control algorithm. And we basically using memristor-based analog circuit to build the small brain. Next slide, please. And so first we use analog common filter for the sensor fusion. Then the signal feed to the PD controller. And yeah, it's also the simplest control algorithm. The PD controller will send the information to the motor driver and to make the motor decide to make the motor to turn to keep this self-standing car in balance. Next slide, please. Well, since I only have 10 minutes plus 1 minute from Professor Yang, it's only 11 minutes. I'm not going to go through details, but this is the circuit for the sensor fusion. This is a common filter, and within this common filter, the common gain actually is implemented using the resistance value of a memristor. And this circuit is super simple, and the entire circuit, the entire calculation is basically RC delay is less than 1 microsecond. Compared with the digital common filter, came originally with a robot, which takes a few milliseconds to do the common filter. The calculation is super simple, but you have to, for your sensor, you have to do analog to digital conversion, then you have to send digital signal through the bus to the processor, then processor do the calculation. So those, you have those overhead, because those overhead, that's why it took a few milliseconds. But here, everything happens in analog is less than 1 microsecond. And the next slide, please. And for the control of the previous one, for the control algorithm, and the control is the simplest possible control, just a PD control, and it's just a reverse pendulum. And in a reverse pendulum, you have this damping term. If the damping is too much, it go back to balance slowly. If the damping is too little, then it keep shaking, also go back to balance slowly. So we implement this PD control also in analog, and then the damping term in the resistance value of a memristor. And at a different memristor value, of course, the performance will be different. Actually, we let the robot to learn how to stay in balance the best by itself. What I mean by itself is basically in the circuit, we just tune the memristor resistance value randomly to one direction. And if to increase resistance, make it more stable, then we keep increasing until there's no change. So in this way, the robot can learn to stay in balance. Well, it can stay to optimize the balance. Next slide, please. Again, I'm not going to go through any details, but here's just a comparison of our technology with some comparison technology. Of course, those digital counterparts, depending on how much money you are willing to put in, you can have very different performance. The best performance is if you're willing to spend a lot of money on FPGA and program the FPGA to do the control. But even for so, our technology is still about 40 times more energy efficient and 16 times faster. But of course, you don't need to just listen to my bragging. And next slide, please. Actually, we have a video to show you. Please play the video. Yes. This is 8 times slow motion on the top. That's it's exactly same self-standing car. On the top, we replace the digital common filter and the digital PD controller with our analog common filter and the controller enabled by memristor. The bottom one, that's the digital one, and you can see the top one go back to balance much faster. And we put Apple to exactly same height. So we make sure the impact is exactly same. If you pay special attention to the wheel, right after the impact, if you pay special attention to the wheel right after impact, and probably you'll notice the bottom one, actually the wheel start to turn with a tiny latency. And that's why, because the bottom one, the digital one, there's a few milliseconds delay, and this actually makes the our approach much more stable. Next slide, please. And of course, for more complicated robotic system, just a simple PD controller no longer works. For example, right now we are building a small brain for a micro drone, and it has 6 degrees of freedom. But for those more complicated robotic system, and typically people using something called a model predictive control. And well, just for the sake of time, we are not going to go through the details. But basically what this does is you want your drone to have some state, but you do a measurement. Most likely it's not exactly state you want. Then you have to do something. And this is a basic optimization problem. And turns out to control a robot, 95% of computation power spending on solving this optimization problem. And next slide, please. And actually, it turns out we actually can build a circuit based on memristor array, actually to solve a constraint optimization problem. If the cost function is quadratic or linear, we can map the cost function and to certain part of the memristor value in the array, and we can map the constraints also to certain part of circuit to the proper value of the memristor array. And then you just connect this circuit to power supply. When the circuit settles, the volume on each column actually represents the answer of the optimization problem. Next slide, please. And right now, and we are working to, or actually making chip, and also with memristor heterogeneous integrate to the chip. And so we can eventually put this on this small micro drone. And this drone actually will size about your hand. And then build this small brain and offload the processor, liberate the processor on the drone to do something more useful. Next slide, please. And this is the team for this micro drone project, and we have all 3 labs working together, including my lab and Professor Chen's lab and Professor Noon's lab in the AME. Next, please. And so basically today I talk about a simple cerebellum, simple small brain based on memristors. And we also showed actually it is possible to use memristor-based circuit to solve optimization problem. And then we are working on more sophisticated small brain based on this QP solver. And thank you. And the work was sponsored by IARPA and AFRL. And thank you.
Thank you, Wei. Thank you very much. And again, people who have questions, please post them in the Q&A. I think we actually have about 10 minutes left in this session, so we have a few minutes for questions. The first question comes from Arvind Dasu. It's for Rehan. And if I can paraphrase a little bit, it's Rehan, you motivated training at the edge, or training more generally, but at the edge, Arvind thinks maybe we care more about inference. And if I just stop there and ask you, what are your thoughts about that?
It's a fantastic question. I think there might also be an additional question in there, but I think that does capture the essence of the question. And I think the answer is, of course, nobody would train at the edge. That's crazy, right? But why is it crazy? It's crazy because of how much power and time it actually takes to do something like that. You would only do this in a data center. And so, the point of the talk was to say, hey, we are approaching these computations using a different approach, and that approach is coupled oscillators and using the frequency spectrum of coupled oscillators. And what that allows you to do is basically carry out highly parallel computations directly when you are actually taking the measurement. And what it also allows you to do, which is not presented here, is potentially operate at 100, maybe even more than that, to 1,000 times more energy efficiently. So the numbers of max per watt could be on the order of above 1,000 multiply accumulates per watt. Tera max per watt, sorry, 1,000 tera max per watt equivalent carried out by these types of systems. And so I think it's a fantastic question, and it exactly highlights the challenge that we have today, which is if you really do want to do things like training, there's just no way to do that in any place other than a data center. There was another question at the end, which said, is there a need for human in the loop for such type of training? I'm actually not sure of what exactly the question is asking. The answer might be maybe, maybe not.
That is also a good question for the panel discussion. I think that as we look to a broader range of folks who are looking at this problem. So hopefully, Arvind, you can post that question later. There's a question from Heidi Ziegler to Joshua and maybe Wei, in terms of the temperature ranges that the memristors can operate. Now, we saw Wei. I suspect that wasn't in a cryogenic robot, so we know it could operate in normal room temperature. But what is the range?
Yeah. That's a good question. In fact, when you cool it down, the behavior is usually better because you have less noise for each level, and the drift become also smaller. And so the price you pay is when you cool it down, it takes a little bit more energy to move the atoms from one location to the other, but it becomes much more stable. So the lowest temperature we have been switch our memristor at was 5K. It's just 5 Kelvin. It's just happened to be the temperature we cool it down at that temperature with our MPMS system. So lower temperature, probably some material close to their superconducting range. So basically lower temperature is okay, very broad range. Then a higher temperature, above room temperature, it highly depends on the materials you are using. We have been using 2D materials to build molybdenum and to be the switching layer. And it turned out that the 2D materials can give us a higher temperature for the operation. And the highest temperature we used, I remember, was over 300 Celsius, 324, something like that. We switch the device at that temperature on and off. And we show the endurance, I think over 1 million endurance for sure. So but for a normal oxide-based material, it's probably cannot go 300 degrees Celsius, but 100 degrees Celsius is fine for most of the oxide-based devices, especially tantalum oxide-based device. Again, it's heavily depending on the materials you are using.
Yeah, so let me before I go to this other question posted, I wanted to bring a question for Jay here related to the temperature. So Jay, you talked about needing to be in fairly cool temperatures, and that does pose a challenge in terms of practically building these systems. You mentioned maybe cryogenic temperatures. I'm curious about the variations in temperatures. In CMOS, we have to make sure that the devices work over a wide range of temperatures. So controlling the temperature at a given, the system at a given temperature tends to be very difficult, if not possible. In these kinds of systems that you're thinking, do you need to control the temperature precisely, or is a range possible, and how would that happen?
Yeah, so that's a good question. So there is a range that you can work with. So where I showed this case where you can leverage two transitions that happen below and above the operating temperature, and that operating temperature could range anywhere from 150 Kelvin to 230 Kelvin or so. Now, this is the specific material that we are studying. We are always looking for other materials that could work at higher temperatures. So in principle, you could do the same thing at room temperature where there is a transition below and above.
How do you guarantee a system is in that temperature range when you're that kind of cold? Is there you put it in some liquid bath? What do you do?
Yeah. So we put it in a cryostat where you can maintain the temperature of the sample, and you can do it. I mean, for measurements is okay, but for practical application, as you said, like the key is to work at low power regime so that you don't have local heating, and hence you start having these drift that Joshua was also talking about. If you have this system work overdrive, you're going to have local heating, and the behavior is going to be uncontrolled. That's a big issue.
Gotcha. Well, yeah, so definitely. Okay, so I think I have time for one more question here. This comes from Arman Kazemi, and maybe to Wei and maybe to Joshua in terms of challenges of memristor-based systems. When we're going to see industrial level adoption for large scale applications. So basically, what are the roadblocks for getting these types of systems in our phones today?
Yeah, so this is a good question. I will answer, then I'll let Wei to add. So this is a very good question, depending on the applications that we are talking about. So traditionally, people using memristor for memory application, then there are a number of challenges, but I would say two showstoppers at least. One is the large variation from device to device, from cycle to cycle for memory application. The other one is for memory application, naturally you want very high density, and you need a selector, very good selector. So, but that's for memory application. For computing application, build a computing accelerator, the requirements are different. First, the variability. Memory, usually you want to have a one shot, you get to the conductance level you want. You cannot afford to do many iterations, switch and verify and switch again to get to your conductance level. But for computing inference application, especially, you don't switch them very often, just during training, you switch them, and then you just let them stay there for inference. Then you can afford to have multiple switching iteration. So then the variability become less issue. And then the density, it's not a memory, it's a processor. So 1T1R, you know, transistor DRAM type of density is sufficient. So then you can see it's ready actually for computing application. You know, especially with the lesson, you know, the result I show, we made it in the fab, and we made it with large wafer and great uniformity. So for computing application, I would say it's ready. But why it's not happening? We just need the mainstream foundry to adopt the process, which has a high barrier, you know. So, but technologically, it's pretty much ready, I would say. Yeah, I will let Wei to add if there are any.
If you can add quickly,
okay. Yeah, that's a great answer. Sorry, my Zoom just crashed, so my video doesn't show up. And I think Jianhua gave a great answer. And a few things, actually, when Memristor was first invented, people think this as a replacement of a flash memory because flash memory going to hit a brick wall, whatever. But then now people stacking more than 100 layers together, and seems like it's okay. And but then later on, people realize Memristor is a great device to implement neuromorphic computing, things like this. And so then the Memristor actually keep going in greater again. And just like Joshua said, one of the problem is there's no major foundry offer the service to put Memristor on it. Actually, TSMC, they offer some service to put Memristor on it, but the type of Memristor they're willing to put on the CMOS circuit doesn't meet the requirement of our application. So in the end, it's really when we are going to have a killer application, need to have Memristor on it, then the major foundry will offer the specific type of Memristor that can meet the requirement. Because again, different group, different lab, making Memristors, and we all tailor Memristor to have a different characteristics to meet our own application purpose. And so it's not like a CMOS. Okay, when we talk about CMOS, basically we all know what kind of things you expect for each technology node. Now it's not really like this, but what will be the one people want the most, depending on which will be the first killer application.
Thank you very much, Wei. And I now pass it back to Yolanda, I think in decent time.
I think it's back to you, Joshua.
Yeah, great. Okay, thank you, Peter, and thanks everyone. This is a great technical session, and I think we are going to have a break, right? And we will be back in, let's see, we will be back for our panel discussion at 11. 8 minutes break. Yeah. Okay, see you in 8 minutes. Yeah.
Thank you.